Hi all, we welcome you guys for our next dynamic tutorial. In the first part we have shown you how to set up VMD and prepare the files for the simulation process. For those setup and understanding, you can view our first tutorial. If you guys have any issues or query, you can log in into our forum. This video is only for the educational purpose. Taking up this one UBQ simulation in non-periodic boundary conditions. For the starting, we will go into the NAMD tutorial folder and open 1:2 sphere and search for the .conf file. Let's analyze .conf file parameters. For complete and better understanding, you can read the VMD tutorial. Once the .conf file opens, we see job description. This is only for the purpose to inform that what actually configuration file is meant for. Adjustable parameters, simulation parameters, integrator parameters, constant temperature control, output name, execution scripts. All these parameters will define how simulation will run depending upon the condition setup for the simulation. Minimization is performed after all the atomic velocities have set to 0. At last, the run command sets the number of time steps over which to run the MD equilibrium. In this case, we have taken 2500, which corresponds to 500 fs. Running the simulation, you can download the NAMD package from the given link. Again, you just register yourself and download the NAMD latest version. We have downloaded 32 multi-core and pasted in the C drive. As you can see on screen, the software is getting downloaded. We have just copied it and pasted it into the C drive. For our convenience, we have changed the name so that it will be very easy to run the simulation. Now for setting up NAMD, we have to set up the environment variable. For this, go into the system properties and give the complete path of NAMD. This will set up the NAMD. As you can see, NAMD has properly set up. Now from the C prompt, come into the 1:2 sphere folder. Every time when you run the simulation, you have to be in the particular directory so that NAMD gets the file which is required for running the simulation. Once you there in 1:2 sphere folder, run the simulation command, which is NAMD ubq underscore ws underscore eq.conf. For this tutorial, we have run the simulation for very short period of time. As you can see, several output files are getting generated. 7 of the output files contain binary data so that coordinate and velocity information may be kept to high precision. Similarly, we can run the simulation in the periodic condition. For periodic simulation, there are some extra parameters which you can see in the config file. For running the periodic simulation, you have to come into 1:3 box folder and then run the same simulation command. As you can again see, the output files are getting generated. There will be several files which will be getting generated during the process of simulation. Now after the simulation has completed, we will be analyzing the molecular simulation. First is the log file, second is the RMSD value, and third is the confirmation of a protein molecule. The final confirmation which will be coming after the simulation process. Again, from the command prompt, you have to go inside 1:2 folder and open the DCD file. First section of the log file indicates the log info, contains the parameter used to run the simulation. After first section, information about the minimization of system is displayed, being with the line labeled with TLC. This line indicates how long the minimization has lasted. After that, the pressure of the system is given. For the present simulation, no pressure output is given because NAMD does not define the pressure for the non-periodic system. For your simulation, using the periodic boundary condition, pressure value will be seen. The end of the file confirms that the final frame of the simulation is being recorded. Now we will be analyzing the simulation. As this tutorial is just for showing the whole process, results might vary a little bit. The whole simulation runs at 310 Kelvin, as you can see from the log values. Now open the VMD and and open the PSF file from the common folder, and from the 1:2 sphere just open the DCD file. As you can see, the whole 10 frames has been uploaded in the VMD. And now from the VMD TK console, open the same folder, that is 1:2 sphere folder, and run the script name as source rmsd.tcl. This command will generate a new file name as rmsd.dat. You can open that file into the Excel sheet and plot a graph. This graph will show the RMSD value of the whole system during the simulation. As we have run the simulation for a very short period of time, these values may differ from the original simulation. Comparing the protein conformation before and after the simulation. The final conformation of a protein, we can identify the initial and the final conformation. What are the changes that has been taken place during the simulation process? For this analysis, firstly open the ubq_wb.psf file from the common folder. Then you can open the ubq_wb_eq.dcd file from 1:3 sphere folder. As you can see, these files have 10 frames loaded in the VMD. You can choose different styles to visualize the simulation and protein molecules with the help of VMD. Now type the command protein, which will show only the protein part of the simulation. From the time frame, you can see the various conformation of protein at various interval of dynamic run. These are the different frames which have been recorded at the different interval time of dynamics. Now for analyzing the conformation of protein, we will save the initial frame and the last frame of the simulation in the PDB format. That is the ninth frame and then the first frame, that is the 0 frame. You can name your protein as per your convenience. Now you can visualize the initial and the final frame in PyMol. Open the PyMol and we have saved our protein frames over the desktop, and you can open all the 9 frames. As you can see on screen, all the 9 frames of ubiquitin, and now we have just selected the initial frame and the last frame. You can analyze the conformal changes which took place during the various time interval of the dynamics. Moreover, you can analyze the final and stabilized protein complex along with the ligand. As you can see, the protein that has stabilized itself, and there are slightly different conformation of the ligand and the protein itself. As in this tutorial, we have run both the periodic and non-periodic simulation together. We can analyze the protein conformation for both simulation. As on screen now, you can see the protein complex over the non-periodic condition, which is protein in the sphere box. This was the first simulation which we have run, and the another one was water box, that was the periodic simulation. Again, you can visualize the protein by different options present in the VMD. One can also identify the differences in the protein molecule between the periodic simulation and in the non-periodic simulation condition. You can again save those files on the desktop or wherever you want, and with the different names. As you can see, we have saved the initial and the final confirmation of the simulation which is in the non-periodic condition, and now we can visualize those protein molecules, the initial and the final frame, again in PyMol. With the help of PyMol, you can see the final ligand and its conformation along with any of the frames which is present. And you can see the gradual stabilization of protein and ligand. I hope you guys have enjoyed this video tutorial. Thanks for watching the video, and if you guys have any queries, you can log in into our forum. Happy innovating, guys. Thanks.